Hello, welcome to our Imperial Science Innovation Competition submission. We are Team Llama. Our idea is using electric fields to extract water from desert fog. The problem we are trying to tackle is UN Goal 6, which is to ensure availability and sustainable management of water and sanitation for all. Nearly 1.1 billion people lack access to safe drinking water, and many more live with chronic water stress, especially in arid and coastal deserts. Some of these regions, like coastal Chile, Morocco, and Namibia, receive very little rain but experience regular dense morning fogs that represent a large but currently wasted water source. Here are some background scientific principles. At any given temperature, air has a limited vapor capacity. When cooled to the dew point, the relative humidity reaches 100% and excess vapor undergoes phase change to liquid via condensation. Solid surfaces that are cooler than nearby air enhance local heat transfer, cooling the near surface air below the dew point and thereby nucleating and growing liquid droplets on the surface. During nighttime, ground temperatures can decrease due to radiative cooling, and near ground air can reach or fall below the dew point, forming fog or dew. Suspended fog droplets and newly condensed droplets then hit and stick the colder surfaces, where they adhere, coalesce into larger drops, and turn into dripping water. Here's a diagram showing radiation fog and advection fog. Advection fog is the reason why coastal areas, where there's warm incoming moist air from oceans, make coastal desert areas the perfect spot for our plan. Let's talk about conventional fog nets. Conventional fog nets are passive plastic or metal meshes placed in the wind near the ground, where water molecules hit high surface area meshes and condense into droplets. They rely purely on inertial impact of droplets on the fiber meshes and typically only capture about 1 to 2% of the water passing through, rarely reaching 10% even with advanced coatings such as atmospheric absorbents. The main bottleneck here is the aerodynamics, since tiny droplets less than 20 micrometers follow air streamlines around the wires rather than colliding with them. Here's a diagram to show you the traditional fog net. Here is our proposed solution. A new concept initially researched by MIT is an ion emitter. In this case, we're going to use a high voltage wire that injects charge into fog droplets via corona discharge. An electric charge between the wires and grounded collector pulls charged droplets towards the wires. Electric forces can overcome aerodynamic drag, forcing droplets to deposit on the collector even if they were not originally headed towards it. Here is a diagram illustrating the discharge electrode ionizing the water molecules and causing them to be attracted to the grounded collecting electrode. In this case, our high voltage wires is our discharging electrode and our grounded mesh is where the water molecules are being attracted to.
So the coronary discharge ionizes the water droplets in the air around the mesh, creating a difference in charge between the mesh and the water droplets, bending their trajectories to allow for a greater surface area of water collection. The deposition efficiency is directly proportional to Ke, which is a dimensionless parameter related to the electric number. This compares the electric forces to the viscous drag, and two important saturation limits that are taken into account in our design are the voltage saturation, because at high voltages, the water molecules can only bend to a certain limit, and the spacing saturation, because if too many meshes are close together, then they will be fighting for water droplets.
The electrostatic fog collection system requires 40 watts per square meter of wire mesh. This translates to approximately 2 kilowatt hours per cubic meter of collected water. In denser fog applications, this figure can get as low as 0.2 kilowatt hours per cubic meter of collected water. Solar panels can be used to provide power to the electrostatically driven fog collection system. Standard polycrystalline panels provide 150 to 200 watts per square meter of panel. Under optimal conditions, each square meter of panel would provide 0.75 to 1 kilowatt hour of power a day. The electrostatically driven fog collection system has three main competitors: atmospheric sorbents, desalination, and aquifers. The electrostatic fog collector requires 2 kilowatt hours per cubic meter of water collected and can produce up to 24 liters of water per square meter of wire mesh. Atmospheric sorbents require up around 4 megawatt hours per cubic meter of water collected and can produce over 50 liters per square meter used by the system. And while that is more than the electrostatic fog collector, the power cost greatly outweighs this gain. Desalination requires 3 kilowatt hours per cubic meter of water collected and can collect up to 15 liters of water per square meter. This is more power and less water collected, and therefore this system is less efficient. And lastly, aquifers. These require only 544 watt hours per cubic meter of water collected. However, depending on the pump site, they can require far more space per litre of water, and by far more costly to set up.
Electrostatically driven fog collection using space charge injection significantly enhances fog harvesting efficiency beyond traditional mesh collectors. The injection of charge into droplets via corona discharge enables active control of droplet trajectories, overcoming aerodynamic limitations. The relationship between collection efficiency and applied voltage follows predictable scaling laws governed by non-dimensional parameters, allowing for rational design. Practical energy consumption is competitive with or better than existing water purification technologies, with scalable applications in arid, foggy environments and industrial water recovery. The work provides a new paradigm for fog harvesting technology combining electrostatics with mesh design to enable efficient low-energy water collection systems.